So when we're doing math and physics, what we like to do is work with scalars, but unfortunately we often have to work with vectors as well. Scalars are easy, we just add them like normal numbers, and adding vectors is actually pretty easy too, in one dimension at least. Okay? So adding vectors in 1D is pretty intuitive. We kind of know how to do this. Okay, if two vectors are going in the same direction, then they're said to be parallel. And these kinds of vectors, you could just straight up add them. And if two vectors are going in opposite directions in 1D, they're said to be antiparallel. So if your vectors are going antiparallel, then you don't add them, you subtract them. Okay. That's pretty easy, pretty straightforward. We can also do multiplication. If you multiply a vector by a number, if you want to increase its magnitude by multiplication, you just multiply it. Just multiply. That's all you have to do to multiply a vector by a number. You just multiply it. That's pretty straightforward. Where things get tricky is when you start moving into 2 dimensions. 2D math on vectors. So for an example, let's say I want to take vector A and I want to add it to vector B to get me some new vector, we'll call it C. I can draw these vectors. I can have A going maybe up like this. I want to draw our little arrow over our vector. I can have B maybe going something like this. Okay. And what I can do is I can actually, I can draw these vectors out and I can see what they look like. And I can do this graphically by doing something called the tip to tail method. So I take a vector, I take its origin, I draw it to its tip, and then the next vector, I want to take this tail of this vector, and I want to attach it to the tip of the previous vector that I'm adding it to, and then draw my vector. So if I were to do this, I'd have my vector A, which kind of is going up and over by 1 square-ish. And then I take the tip, the tail of my previous vector, of my vector B, the one that I want to add, and I put the tail of that at the tip of the A vector, and then I draw this vector down. And it goes something like this. So there's my vector B, and then my resultant vector is going to be from the beginning of the first vector to the end of the last vector. And this, I'm only adding 2 vectors. You can do this with multiple vectors. Okay. Doing this is a little bit tedious. Having to do this with graphical format is a little bit tough, right? You have to get a ruler, you have to get a measurement, you have to get graph paper, and you have to be very precise. So what we want to do is we want to kind of know how to do this analytically. So you want to do this without having to graph. So how do we analytically figure out these kinds of vector addition problems? So what we want to do when we're adding vectors is we want to think of vectors like Vegas. Okay. What we know from ads about Las Vegas, what happens in Vegas stays in Vegas. The same thing is true for vectors. What happens in X direction stays in the X direction. And what happens in the Y direction stays in the Y direction. They're independent of each other. So I can only add things in the X direction with other things in the X direction. Okay. This process of adding vectors in 2 dimensions, adding only the X in the X direction and only Y stuff with other Y stuff, this is critical. I cannot emphasize how important it is that you get good at doing this stuff. You have to be able to do this. You will not pass physics if you cannot figure out these kind of vector notations. So this is very, very fundamental. So let's draw a coordinate system. So I'm going to draw an X and Y axis. Okay. So here's my X axis, here's my Y axis. And then I'm going to take that and I'm going to draw a vector. So I start my vector and I'm just going to draw it upwards like this. So there's my resultant vector, vector A. And it has some little bit of it that's going in the x direction and some little bit that's going in the y. I'm going to say that this has a magnitude of length 10, and I'm going to say that it's moving at an angle theta equal to 30. If I want to break this into the x and y directions so that I can start doing some math on this, so I can actually start decomposing this, the first step I need to do is I need to make a right triangle up here. So step number 1 of this process of adding vectors, it's called decomposing a vector, is to make a right triangle. Not a wrong one, we want to make a right one. So to do this, I can make a right triangle right here. If I come over a little bit, I imagine walking kind of entirely along the x-axis a little bit till I get right underneath this tip. Once I'm right underneath there, I walk as far as I can in the x. And we'll call this A in the x direction. Okay, and we'll denote that as a vector, and we're going to call this magnitude of ax, and we're going to associate this with something called the little I hat. So we'll see what that I hat is in a second. And then I'm going to go from this tip along the x-axis, and I'm going to go upwards, and entirely upwards, till I get to the tail, the tip of my original vector A. And I'm going to call this, we'll call this AY, and we'll say that AY vector is equal to AY, whatever the magnitude is there, in the J hat. So what are these little I hat and J hat? What the heck does that mean? These are things called unit vectors. Unit vectors are really, really useful. It's a way you associate a direction without changing the magnitude of something. Unit vectors have a magnitude of 1. And we have some standard unit vectors we use. If something is going in the x direction, we say it has the unit vector I hat. If something is going in the y direction, we say it has the unit vector j hat. If something is going in the z direction, it has the unit vector of k hat. So we have I, j, and k. And now what we want to do when we start figuring this out, we start decomposing this vector, we want to write out a whole bunch of trig functions. So write the trig functions that associate with this triangle that we've just drawn. So we have a few different trig functions that we should be pretty familiar with. We've got the sine of theta. And if I look at this plot, here's my theta. The sine is the opposite side, which is going to be the far side over here, this AY, over the hypotenuse, which is going to be A. So sine of theta is equal to AY divided by A. And I could do a little bit of math on this, right? I could do some trigonometry, or some algebra rather, and I can multiply both sides by A to get AY by itself. I get rid of the A's on the right-hand side, and I am left with AY is equal to A times sine of theta. So now I know what the A is, how much of A is going in the y direction. I can plug in the numbers that I have. I can plug in 10, multiply it by sine of 30, and plug this into your calculators now so that you can find and make sure you are getting 10 times 0.5, which is equal to 5. Make sure you are getting this in your calculators. If you are not, your calculator might be in the wrong mode, and we need to fix that now before we get too far into the semester. Okay, let's do another trig function. We can do cosine of theta. Cosine of theta is the adjacent side over the hypotenuse. So again, here's my angle. The adjacent side is the side that is connected, is attached to this angle. So I have two sides. I've got this side along the x direction and this side along the hypotenuse. So that should clearly tell us that cosine of theta is ax divided by a. I do my algebra. Multiply both sides by a to get ax by itself, and this gives me the a's canceling on the right-hand side, so that ax is equal to a times cosine of theta. Plug in your numbers. Do this in your calculator. 10 times cosine of 30 is equal to 10 times 0.5.